Hi, welcome to Complex Analysis. This is the fourth session on Laurent series. Today we are going to give a function and we want to find its Laurent series in an annulus. And this example, we will also make use of this example to illustrate various results which you have learned in complex analysis. Now, the example may look easy, and this is one of the standard examples. You will see that a typical what I call algebraic manipulations will immediately give the result, and people are happy, you will get marks. But there is a lot of things which we can learn from this. As you know, my idea is always to delve deeper, understand in depth. So we will use this example to do that. Okay, let us get started. So the example I want to look at is this. F is a function which is defined as f of z. This you will find very standard example, z minus 1 and 2, z minus 2, this is 2. Therefore z is in c minus 1 and 2. Okay, right. Now as you know, f is holomorphic on this domain. Right. So when I want Laurent series, notice that first I have to fix an annular. So we want to find annulus on which f is holomorphic and find the Laurent series there. Right. And usually what will the textbooks etc. and teachers will give you, they will also give you annulus and ask you to find the Laurent expansion. But you should learn, given the function, what are the possible annuli. Okay, there may be more than one. For example, here I want an annulus, therefore the easiest thing is if I assume something like z, okay, mod z is 1 less than mod z less than 2. Okay, then z equal to 1 is ruled out, z equal to 2 is ruled out. Therefore on this annulus, okay, this set of all z in complex numbers is this. Okay, f is holomorphic. Right. Okay, now there are also other annulus, so let me call it as a1, and there is another annulus a2, which is, just look at z minus 1. So I have 1 here, this is my 0, the complex plane I am 1. So if I just take this, okay, less than 1, okay, z minus 1, 0 less than 1 less than 1, then in this annulus also f is holomorphic and it has an essential singularity at the center here, whereas at the center of this annulus is 0. There is nothing wrong with the function there. Okay, in a neighborhood of 0 it is actually holomorphic. Here it is not the case. Okay, and there is also third one is it is mod z greater than 2. So you avoid everybody. So I have 2 and take the closed thing and throw it out. So this is my domain A3. Okay, check whether there are any possible any more annulus. Okay, exercise, are there any more? So you notice that whenever I wrote that, you can also say 1.5 to 1 1/4, 3/4, 1.5 less than mod z less than 1 3/4, etc. So you don't say that's a new annulus, right? You understand what I mean. In some sense, the annulus should be maximum possible on which the function is going to be holomorphic. Okay, so first let's look at annulus 1. So annulus 1 is 1 less than mod z less than 2. So what is the center of the annulus? 0. Therefore, okay, Laurent series should involve powers of z power n, where n may be in z. Okay, these are the kind of things you should do. For example, in the case of A2, the center of the annulus is 1, therefore my power series should be in the powers of z minus 1, something like z minus 1 to the power n, wherein it could be any integer. And let's look at A3. What is the center of the annulus? This is same as, remember, 2 less than mod z less than infinity. Therefore, center of the annulus is 0. Therefore, here also I should expect the powers of z only, that is z power n, wherein is in integer. Okay, these are the first thing. Before started computing, you should have a clear-cut idea of what kind of powers you are looking for. Therefore, you can do the manipulations correctly. Okay, let me just see whether I had screen share. Okay, so let us look at z minus 1, right? Okay, so the function f of z, the first thing is, as I said, first algebraic manipulations. See, in all the cases, what you do is you either use binomial series, try to manipulate things so that you can apply binomial series, or you already have well-known expansions like the elementary functions, like exponential function, trigonometric function, hyperbolic functions, etc. Okay, make use of those things, and then finally use the uniqueness of the Laurent series. Therefore, the whatever you got by algebraic manipulation, that will be the Laurent series because of the uniqueness of Laurent series. Okay, I'm going far ahead. You should read from my books if you want. Okay, I'm just giving the idea of all these things. Okay, this one obvious thing is you do the partial fraction, z minus 2 by 1 by z minus 1. I hope I'm correct. Yeah, z minus 2. This is z minus 1 minus of minus. Yeah, therefore this is correct. Is that okay? So now let us look at 1 by z minus 2. See, here mod z is less than 2, right? So I want, as I said, I want a geometric power series, right? Therefore z minus 2, okay, let us look at this. This, what I can do is I can take 2 out. Z minus 2, I can take 2. If you want minus 2, 1 by z minus 2. Is it okay? Yeah. Therefore, 1 upon z minus 2 will be minus 1 by 2 and 1 by z by 2 inverse. Therefore, this I have a power series expansion for this. Yeah, the power series expansion is minus 2 summation n equal to 0 to infinity, okay, minus 1 to the power n z power n by 2 power n. Therefore, it's going to be 2 to the power minus n plus 1 into z power n equal to 0 to infinity. Yeah, right. Yeah, before going Laurent series, okay, I should have done something, but let us do it anyway. So this is one. Now let's look at minus 1 by z minus 1. Okay, now here, see, mod z is less than 2. Here mod z is greater than 1, right? Because if z is in the annulus 1, mod z is greater than 1. Therefore, I should take z minus 1. Okay, I will take z out. Okay, therefore 1 by 1 minus z. Right? Therefore, minus 1 by z minus 1 is going to be minus 1 by z into 1 minus 1 by z inverse. That is going to be minus 1 by z and z power minus n equal to 0 to infinity, which is going to be minus, okay, z power minus n minus 1 n equal to 0 to infinity, or it's going to be minus z power n, okay, z, if you want, z power minus n equal to 1 to infinity. Yeah, are all of you happy now? So my f of z is therefore given as, okay, n equal to 0 to infinity of 2 to the power minus of n plus 1 z power n and minus of z power minus n equal to 1 to infinity. If you want the usual way, you may want to write it 1 to infinity of z power minus n plus z power minus 2 power minus n plus 1 into z power n. I don't know, I hope there was no minus sign. Or there a minus sign? Yeah, see here there was a minus sign which I forgot, therefore there is a minus sign throughout. Okay, pause, review, proceed. So see what we have done, right? We simply manipulated, we looked at the terms z minus 2 etc. We saw mod z is less than 2, therefore 2 should come out, then did that, then the usual geometric series. So this is what I call simply manipulations. Okay, you got it, right? But is there a lot more? I want to say in this example we can learn a lot more. What are the things? First, notice that whenever I have a function f, how do you remember the Laurent decomposition? So what is the Laurent decomposition for this? Remember, we got it as z minus 2 minus 1 by z minus 1, and the annular, the region is 1 less than mod z less than 2, right? Now notice that this function 1 z minus 2 is holomorphic on b02. This is your r1, this is r2, so this is already holomorphic, therefore I can take this to be f2. Okay, now let us look at this one. If I take minus 1 by z minus 1, that is holomorphic outside b01 closure. Therefore I can take this to be f1 of z, and also note that, okay, minus 1 by z minus 1 goes to 0 as z goes to infinity. Okay, therefore the Laurent decomposition f equal to f2 plus f1, where f2 is 1 by z minus 2 and f1 of z is minus 1 by z minus 1. That's the Laurent decomposition. Yeah, right. And second, remember we have learned in the Laurent series expansion, if I write f of z in the annulus as summation cn z minus a to the power n, n running from minus infinity to plus infinity, then cn are given by 1 by 2 pi over some circle gamma which is in the annulus, such that f of w by w minus a to the power n plus 1 dw, right? So one way of saying to compute the Laurent series may be to find out cn's. Okay, find cn's. Okay, but as you know, integration is always difficult. Estimating integrals is easy, it's always very difficult, and there too path integrals, right? So you know it's a tough, right? But in this case, let us see whether we already found out what cn's are, right? What are our cn's? Let us go back. So in this case, cn's are going to be, if n is positive, cn is going, cn is, n is non-negative, then cn is going to be minus 2 to the power minus 1, that is minus 1 by 2 power n plus 1. And when it is negative, it's going to be minus 1, right? Right? Cn equal to minus 1 by 2 power n plus 1. I hope I am right, just to make sure, and equal to minus 1 if n is less than 0 in this case, right? So we would like to see whether we get it. Okay, you see that how easy what we did? It's purely formal manipulation. Okay, now this is going to be tough, so let's try to do that. Okay, so what is that we want? Let us look at the function f of w. So f of w is 1 by w minus 1, w minus 2, and by this is w power n plus 1 because my a is 0 here, right, into w power n plus 1. This is my upper w, right. Now what is the natural thing again? So I want to say integral of this fellow, path integral of this. So again it's easier if I break this into partial sums, partial fractions rather. So break into partial fractions. Okay, then you just find the path integrals, right, because path integral is linear, right, therefore let us do. So how will I do that? 1 minus w1, this is what I said, you will learn a lot of things which you usually do that. So this I can write as a1 by w minus a1 plus a2 by w minus a2 plus, let us say, b1 by w plus b2 by w squared plus bn plus 1 by w power n plus 1, where a1, a2, b1, bn plus 1 are to be found. Okay, so I'm kind of making this as a fact that we know it's any such thing we can have a partial fraction expansions. In fact, you will see in the next series on residue theorem, we will actually prove that partial fractions, the existence of partial fractions, we will prove that. But from your integration days, you would have learned that you can always do that. Okay, you know, given a thing fraction, you know how to write as a sum of partial fractions, right? That we are just making use of that. Okay, don't be intimidated. I'm just saying. Okay, you know how to get it. Like, I mean, you given a real number, positive non-negative real number, you know how to compute the square root, right? But it required analysis to prove square roots for non-negative real numbers exist. Do you understand the difference? So similarly, given this kind of a fraction, you know how to find the partial fractions, but somebody should assure you for any such thing there is always a partial fraction expansion. Okay, that will be done later. In this case, we are actually going to give the partial fraction expansion. Let us do that. The first thing is, okay, luckily we do not have to worry about lot of things, because let us look at a2 by w minus 2. See, therefore integral, the path integral over this, okay, this will be path integral over this, okay, but path integral is going to be linear, therefore path integral over this, path integral of this, path integral of this, etc. Now notice that a2 minus w2, so my path integral over gamma, so remember I can take this is 2, therefore I can take some path to be like this. This is my path gamma, right? And my 2 is outside, and therefore this function is holomorphic inside this disk, right? It's going to be holomorphic here if you want another open set also, therefore this is going to be 0, right? Do you understand this? This is by Cauchy's theorem. See, this is what I said. We will be using a lot of earlier results, so you will feel better. See, how do I apply? See, this function 1 by w minus z is holomorphic on and b0 r dash, where r dash is greater than r, where this is gamma equal to gamma r. Okay, right? And therefore I can apply Cauchy's theorem for this star shaped domain, therefore it's going to be 0. Now let's look at the other fellows. Now I am saying if k is greater than or equal to 2, now bk by w power k over gamma, that's also 0. Why? Because again 1 by w power k has a primitive, where again in b0 r dash if you want. Therefore, okay, namely w power minus k and so on, that will be primitive. Yeah, so this as a primitive, we had already seen this kind of thing, therefore this integral is 0. Pause, review, proceed. Because what all I need is w power minus k plus 1 by minus k plus 1. Therefore, if k is greater than equal to 2, this is non-zero. Therefore, this is a primitive. Right? So, what does it mean? That means I don't have to worry about what is a2, what is b2, b3, bn plus 1. I only have to find out what is a1 and b1 to find this integral. Do you understand this? Therefore, this integral is going to be this integral and this integral. Whereas these things integrals do not matter. You follow that? You see that you will be learning a lot of analysis, complex analysis here. Okay. Now, how do I find a1? Let us look at. So, what do I have? I have 1 by w minus 1, w minus 2 into w power n plus 1. I am having a1 by w minus 1 plus a2 by w minus 2, etc. b1 by w plus bn plus 1 by w power n plus 1. I hope I am doing it correctly. Therefore, multiply both sides by w minus 1 and then let w equal to 1. These are the things which you will learn in your 12th standard integral calculus. Right? Therefore, what is this side? This side is going to be 1 by w minus 2 into w power n plus 1, where w equal to 1. Therefore, it's going to be minus on this side. Yeah, and here it is going to be a1 into w minus 1 by w minus 1. Therefore, it's a1. All these things will go to 0. Therefore, my a1. Okay, this implies a1 is minus 1. Right? So, as I said earlier, I only need to compute b1. So, what is the trick? Now, let's again see that. To get b1, what do you think I should do? I should multiply by w, right? That is, call this as, if you want 1, multiply 1 by w and then let w go to infinity. Because when w go to infinity, these fellows will be 0. Right? But there is a problem. Do you see that? When I get w go to infinity, what do I get? So let's do that. So I'll have w by w minus 1, w minus 2 and w power n plus 1. Therefore, it is w power n equal to, now you can see this is going to be a1 w by w minus 1 and a2 w by w minus 2 plus b1 w by w, etc. and b2 w by w squared and bn plus 1 w by w power n plus 1. Therefore, when I let n plus 1 w go to infinity here, then what I get will be this goes to 1. This goes to 1. This is equal to 1. Therefore, I get a1 plus a2 plus b1. Right? These fellows, all other fellows will go to 0. Each one of them go to 0. And this also goes to 0. Therefore, I get a1 plus a2 plus b1 equal to 0. So, I don't get b1. But I already know a1. You understand that? Therefore, so it's necessary, we need to find a2. See, look at that. We said that earlier, we didn't need this integral, but unfortunately we still need a2. Luckily we don't have to worry about b2 to bn plus 1. Hopefully, right? We already found it. Yeah, because I have found a1. If I find a2, then I know what is b1. b1 has to be minus a1 minus a2. Okay, right. So what is a2? But a2 is easy. So again, let's look at what is the function. That is 1 by w minus 1 w minus 2 into w power n plus 1. Therefore, multiply this is equal to a1 by w minus 1 a2 by w minus 2 plus b1 by w, etc. So multiply this by w minus 2. Okay, therefore I will have 1 by w minus 1 into w power n plus 1. Yeah, are you following on this? And then evaluate at w equal to 2. When w equal to 2, this is going to be 1 by 2 to the power n plus 1. Do you understand this? Yeah, okay. Now when I do here, what do I get? So when I multiply this by w minus 2, okay, and then put w equal to 2, this goes, therefore I will get a2. I hope I did correctly. W minus 1 minus w minus 2, w power n plus 1, w minus 2 I am multiplying, therefore I get w minus 1. Yeah, right, therefore it's 2 minus 1, 2 to the power n plus 1. Okay, I hope I am right. And when I multiply these things, they will get, therefore a2 equal to 1 by 2 to the power n plus 1. Right, now what do I have? a1 plus a2 plus b1 is 0, and a1 I know what it is. I hope it is minus 1 plus a2 is 1 by 2 to the power n plus 1, right, equal to minus b, that is b equal to 1 by 1 minus 2 to the power n plus 1. Okay, I think I made some mistake. Let me see that. Because I would like to see, I don't think there was a 1. Look at that. What did we have our thing? Yeah. So I know a1 by w minus 1, etc. Right, okay. Okay. 1 by 2 pi I will get, therefore I will get only a1, and then I will get b1. Yes. Let me just see. I'm right. Therefore my Cn is going to be, okay, integral of fw by w minus 1 w minus 2 into w power n plus 1 over gamma, right. We are assuming n is greater than or equal to 0 now everywhere. Okay, therefore this is going to be, we saw integral of a1 by something w minus 1 dw, okay, and a2 by, a2 was not there, b1 by w dw with a 1 by 2 pi I here and 1 by 2 pi I here, right. And therefore this object we know is just a1, okay, and this object is b1, and a1 we know is minus 1, and b1 we know is 1 minus 1 by 2 power n plus 1, therefore minus 1 by 2 power n plus 1. I got it. I'm sorry. I forgot. Yeah, that's what was bothering me. I hope I am recording. So we found out Cn to be minus 1 by 2 power n plus 1 for n greater than or equal to 0. Let me just make sure that that's what we got. Yeah. This is okay, got, right. Now the next thing is we want to find out Cn if n is negative. So again, what is the integral? Cn equal to 1 by 2 pi I integral over gamma of f of w by w power n plus 1, that is integral over 1 by 2 pi I. Let me just put the 2 pi I here so that I don't have to keep worrying. So f of w is 1 by w minus 1, w minus 3 into w power n plus 1. Okay, n is negative, therefore let me put n equal to minus k positive, right? Therefore this is going to be dw. And notice that the gamma, okay, gamma 1, the trick is, let us see. So what do I want? I want n, okay, therefore w power n plus 1 will be equal to w power minus k plus 1, therefore it is going to be w power k minus 1 by w minus 3 or gamma by w minus 1. So w minus 2, right? Yeah, dw. Okay, call this function as g of w. Now notice that g is holomorphic on B02, right? And gamma is the closed path in B02, right? Therefore this is Cauchy type integral formula. This is a Cauchy integral formula for this function, therefore it's a value of this function at 1. Therefore my Cn for n negative is going to be 1 by 2 pi I of integral g of w by w minus 1, where g of w is w power, let me write carefully, k minus 1 by w minus 2. Therefore this is equal to g at 1, but g at 1 is going to be minus 1, right? When w equal to 1, this is minus 1, that's it. Therefore all my Cn's are either C minus n or minus 1 for n power. So let us just make sure that we got it correct. Yeah, this one. So go through this example. You see what are the things we learn. This example is pure manipulation, is much easier. We got it. But then from theory we want to write down the Laurent decomposition of the function, right, in the annulus. That we got it. And third, we also verified the integral formulas for Cn's are correct. We get whatever Cn's we got, it is the same one as we get by using the integral formulas for the coefficient Cn. And in computing the coefficient Cn, you can see what are the things we used. We have to use partial fraction expansions, and then we have to talk about Cauchy's theorem, Cauchy integral formula, and various results, right? So that is a very, very educational instructive exercise example. Please go through it again and again, okay, at least once or twice, so that you get it. Okay, now let's look at the Laurent series expansion for the other two annuli. Here I will be brief. Okay, so the other annulus is A2 was 0 less than mod z minus 1 less than 1. So I have 0, 1. So I am having this. So it's a essentially punctured disk. 1. Therefore, the center of this annulus is 0. Therefore, I should look for powers of z power n in the Laurent series. Okay. So our function f of z is 1 by z minus 1 into z minus 2 equal to 1 by z minus 2 minus 1 z minus 1. Okay, now let's look at what is the power. The annular region is a of 1 0 1. This is a b dash of 0 1, that is center at 1. Okay, smaller radius 0 and bigger radius 1. Okay, therefore this point is removed. That's all it means. Okay, so what is the what is my R1? This is my R1, this is my R2. So what I am looking for, I want to look for f equal to f2 plus f1. Okay, so f1 should be holomorphic outside this, that is b of 0 R1, b of 1 R1, which is, this is nothing other than singleton 1, right? Now you look at z minus 1, this is holomorphic on c minus singleton, right? Therefore my f1 is going to be 1 by z minus 1. Therefore f2 is necessarily 1 by z minus 2. And notice that this is holomorphic. Okay, it should be holomorphic where? In b 1 1. 2 is outside this, therefore this is holomorphic in the, this is your a, this is BAR2. Okay, therefore that is a decomposition, Laurent decomposition. Therefore is f of z equal to 1 by z minus 2 plus minus 1 by z minus 1. This is my f2, this is my f1. Okay, now I want Laurent series. So let us look at this function z by 2, right? Now remember, center of the annulus is 1 and the powers of z minus 1. Okay, see, I already made a mistake. You see that? Yeah, right? This is b dash, therefore the center is 1 and therefore the power should be z minus 1. I'm sorry for the goofing. Therefore let's look at z minus 2. I want z minus 1, therefore obvious thing is z minus 1 minus 1, right? Now notice that my thing is mod z minus 1 is less than 1, therefore I can write this as minus of 1 minus z minus 1, right? Therefore 1 by z minus 2 equal to minus of 1 by 1 minus z minus 1. Therefore this is going to be minus of z minus 1 to the power n equal to 0 to infinity. Is that okay? Right. Next, and let us look at f1. f1 of z is already 1 by, minus 1 by z minus 1. This is already minus of z minus 1, right? So this is already in powers of z minus 1. Do you follow that? Right? Therefore my f of z is going to be minus n equal to 0 to infinity of z minus 1 to the power n and minus of 1 by z minus 1. So this I can rewrite everything as n equal to minus 1 to infinity with a minus sign z minus 1 to the power n. Okay, so this is the Laurent series for f in the annular region 0 less than mod z minus 1 less than 1. So just again go through this. I am sorry for this goofing. Okay, just now I had lunch, so my brain is not working at the best. Hi, let's Now look at Laurent series expansion of that function in the third annular region. It's exactly similar, except uh, I hope I don't get confused with thing when I'm doing computations. 3, my annular region A3 is mod z greater than 2, that is same as 2 less than mod z less than infinity. Therefore, what is the center of the annulus? Center is 0. Okay, I hope I didn't make the mistake which I did in the last example, right? Therefore, the powers, okay, Laurent series should be in powers of z power n, right? Okay, and what is the function? Let's look at this. Is 1 by z minus 2 minus 1 by z minus 1. And now what is our r1? R1 is 2, r2 is infinity. Therefore, r1 complement, that is b0 to complement, and this should be b0 infinity. So my f1 should be holomorphic here, and f2 should be holomorphic here. But let's look at this. Outside this disk b02, these are holomorphic. Therefore, my f2 is actually f, because this is holomorphic on p of 02 complement. Therefore, my f1 must be 0, identically 0. And also notice that, sorry, not f, I'm sorry, I call this f1, right? Yeah, this should be f1. Yeah, f1 must be holomorphic and f2 must be 0. Is that okay? Okay, right. And notice that f1 goes to 0 as z goes to infinity. Therefore, f equal to 0 plus f. Okay, this is my f2, this is my f1. Okay, this is if you want, yeah, this is the Laurent decomposition of f in A3. So this example is, as you can see, is very illustrative. Okay, and the center of the annulus need not be an isolated singularity, because that's a common misconception many students have, because Laurent series usually they associate with isolated singularities. Okay, but remember, Laurent series has nothing to do with that. I want only holomorphic function in an annular region. And second thing, therefore, given the annular region, the same function may have different Laurent decompositions and different Laurent series, and the way we arrive at. Okay, that is why I consider this example to be very nice, very simple minded example. Okay, but there is a lot of things which you can learn from them. So now let's look at this. So 1 by z minus 2, so I want to find the thing. Okay, so this I want in powers of z. Therefore, now remember, mod z is greater than 2. Therefore, I should pull out z out, and then 1 minus 2 by z. Therefore, 1 by z minus 2 equal to 1 by z into power 2 by z power n running from 0 to infinity. Therefore, it is going to be n running from 0 to infinity of 2 power n into z power minus of n plus 1, right? So if I put k equal to n plus 1, therefore my n is k minus 1, and when n is 0, k equal to 1. Therefore this I can rewrite as 2 power k minus 1 z to the power minus k running from 1 to infinity, right? Now let us look at z minus 1. Again I have to take z out, therefore 1 by 1 minus z. Therefore minus of 1 by z minus 1 is minus of 1 by z summation 0 to infinity z to the power minus k. Am I doing it correctly? Yeah, right. Therefore it's going to be z to the power minus k plus 1 with a minus sign, k equal to 0 to infinity, or make it n if you want. n, therefore put k equal to n plus 1 again. Therefore when n is 0, k equal to 1, therefore this is equal to minus z power minus k equal to 1 to infinity. Therefore the Laurent series of f is going to be, let me just make sure, yeah, k equal to 1 to infinity of 2 power k minus 1, okay, minus this one minus 1 into z power minus k. Right, notice that here only the principal part, okay, there no holomorphic or what they call regular part of the Laurent series, that is 0. Okay, so you can, again you can see the way we got different kinds of Laurent series. Okay, in this second annulus we got only, if I remember right, 1 upon z minus 1, that's only negative part. After that everything is positive part, z minus 1 to the power n. Here we have no positive part, everything is negative, and the earlier one we had a mixed. Okay, so you can see there is a lot of variety. Okay, please go through these examples, and as I said, everything is just some kind of manipulation in Laurent series. But if you go through this kind of example in depth, you will understand the concepts very well. Before I finish off, okay, I leave an exercise. Do you remember A1 case what we did? We checked the formula for Cn is the same formula which you got by manipulation. Do something similar for the function f of z equal to z minus 1. So what do you have to do? You have to find its domain, and you have to find the annulus. Okay, which annulus you want to work. Okay, right, and then write the Laurent series and verify. See, e power z is very easy. E power z you can write as e power z minus 1 into e, or e power z minus 1, you know, this is e into z minus 1 to the power n by n factorial 0 to infinity. That's it. Therefore 1 by z minus 1 multiply, right? Therefore this is going to be e into z minus 1 to the power n minus 1 by n factorial n equal to 0 to infinity. Okay, now you make a change of variable, put k equal to n minus 1. Therefore when n is 0, k equal to minus 1. Therefore it's going to be e k equal to minus 1 to infinity z minus 1 to the power k, and n is going to be k plus 1 factorial. So we got it simply by manipulation. Okay, now I got by powers of z minus 1, so you know what is the center of the annulus. Okay, what is the annulus? Describe and use the formula for Cn, integral formula for Cn. Right, to check what you get here is correct. This is much easier than the exam which I did. Much easier than the exam which I did. I worked out. The only idea is that, you know, I used Cauchy integral formula, Cauchy's theorem, and if it has a primitive, then integral over closed path is 0, all those kinds of things. Okay, not all of them may be needed, but that kind of idea you can just revisit in this simple example. Okay, and the last one before I conclude is this. See, let us look at f of z equal to sine 1 by z. This is also another one standard example. Okay, remember sine z is, if I remember right, minus 1 to the power n, z to the power 2n plus 1 by 2n plus 1 factorial, n equal to 0 to infinity. Right, therefore what do I do for the Laurent series? As I said, simply manipulation. In place of z you write 1 by z. Therefore I will have minus 1 to the power n, okay, and So this is going to be z to the power minus of 2n plus 1 by 2n plus 1 factorial. This is n equal to 0 to infinity, right? Therefore this is the Laurent series of f, where in which is Annulus you find out. Okay, right? Now what is the power, what do we have? Therefore ck we have is minus 1 power n by 2n plus 1 factorial if k equal to 2n plus 1 and is 0 otherwise. Okay, and this is minus of 2n plus 1. Sorry, notice that means there is no ck for k positive is 0 and ck negative is also 0 if k is even. Only k odd we have this, right? Now what is the formula for this then? Ck is going to be 1 by 2 pi I sine 1 by w, right? Then I want the case of this is ck equal to 2n plus minus 2n plus 1, right? So what should be the formula for that? Remember my cn formula is 1 by 2 pi I integral over gamma whatever that thing is w minus a, in this case it is 0, therefore w to the power n plus 1 dw, right? Now this is power is minus 2n plus 1, therefore it's going to be w power 2n plus 2 dw. Okay, this if you want take any thing, this is around 0, this is your gamma. Okay, therefore this object is nothing other than minus 1 to the power n by 2n plus 1 factorial, where k equal to 2n plus 1. Okay, so what I am arriving at, I am going a little fast because time is running out. See, by manipulation I found out what is ck if k is minus 2n plus 1, right? Yeah, here I made a mistake. Yeah, so let me go slow. Therefore ck equal to minus 2n plus 1, therefore ck is going to be 1 by 2 pi I over gamma f of w by, okay, w power k, right? That is going to be 1 by 2 pi I integral k, sorry, k plus 1, that is going to be f of w. Okay, what is k? K is minus 2n minus 1, therefore k plus 1 is equal to minus 2n, therefore it's w to the power minus 2n. Okay, therefore it's going to be 1 by 2 pi I integral over gamma of sine 1 by w and w to the power 2 dw. This object is going to be minus 1 to the power n by 2n plus 1 factorial. Yeah, right. So what we have got is, by manipulation we found out cn, and hence that allows us to compute an integral, a path integral of this kind. It may be very difficult, to compute directly. Okay, but a more interesting example is found in my book. So what is the purpose of this? This means to compute the Laurent series you have to compute ck, that means you have to compute certain path integral. But what this example shows is, a path integral may be very difficult looking, but it may turn out to be the kth coefficient of a Laurent series, and that Laurent series may be easier for you to find. Okay, that is the basic idea. I hope you enjoy. Please go through it. And this slightly longer session. Okay, I took a break for lunch, so it was slightly delayed, but I hope it's all fine. Please go through it. I hope you enjoyed. And these three exams are good enough. After that, you look at any book, there will be a lot of computational examples like a calculus thing. You can keep on doing. But I chose example which illustrate the concepts also well and all the in-depth study. Okay. I hope you enjoy. We'll meet again.